Hey, mic's good. This should be recording. Cool. So my name is Joshua Guto. I work for C Labs, and today I'm going to be talking about block execution and state in Geth. So a little about me. I work on the CeLo blockchain client. We're a fork of Geth, EVM compatible, a lot of changes to support mobile users. And some of the various extensions we've made and I've worked on in various ways are proof of stake system based on IBFT. And then we have a lot of governance contracts that set core blockchain parameters like gas price, like the maximum gas in a block is one example. Our election is run through smart contracts. And so I've done some performance work about looking at how we use these interactions. So that's some of the performance work I've done with our client. And today I'll be talking about some performance work specifically around running transactions and how state factors into that. Cool, yeah, so role of state. It's not really going to touch too much onto the problem of, okay, you run all of these transactions, now you have to keep all of the data, and so state growth, that's a big problem. I have some thoughts on it, but that's not really what this talk's going to be about. This got rescheduled, but it was initially about half the time talking, half the time is hands-on component. I was hoping to make a lot of the data that I used in this available to everyone, but we can do that. It's going to take me a little bit to set up because I'm expecting a little more time. So the talking portion is going to be going through some crazy ideas I had. Can we make execution faster? And then the process of going through instrumenting Geth, figuring out, is this something that's viable? Also, if you have questions on anything, please let me know. And then there will be some background sections. If you're bored, tell me. If you don't know what's going on, also tell me. Cool. So the idea is you want to reduce the time spent in state access. It's the bottleneck. Everyone just assumes it. It is actually the bottleneck. And so that's the problem. One idea that's been floating around, I am not the only one that's had it apparently, which is awesome, is that can you parallelize transaction execution? For this, if you could have transactions that were completely separate in the state they modified, then it's trivial to parallelize them. You should run them perfectly in parallel. Unfortunately, that's actually less interesting from a user perspective. It's like the functional programming thing, where if you don't have any state, it's a beautiful program and it does nothing. And so being able to interact with exchanges and DeFi are all really cool things, but it involves multiple people touching the same state. And so to actually be able to parallelize transaction execution, there's a couple different models you can use. One of them that I'm exploring a little bit is a speculative model. Where you want transactions generally to have different read-write sets, but if there's a conflict, you just throw out the second transaction and then rerun it. And the reason this actually works, or probably could work pretty well, and this is why I'm really exploring this, is that if you run a transaction, and just by doing it, you'll load all the memory it touches into a cache somewhere, and I'll talk about all of the cache hierarchies in Geth. There's a lot of them. So because of the way operations are priced, if you're familiar with dodging the bullet with state access, gas price for access is now 2,600 gas. That's still probably underpriced relative to what a stack operation costs. And so that means that because the computation is cheap, and we're probably not doing a huge amount of it, you can just rerun the transaction, and then everything will be in RAM, so it'll be a lot faster. That's the theory, and so the question is, does this work? Yeah, we'll get to that later. So to go through this, and I talk about state models, go through how I instrumented this code to try and figure out the answer to this question, go through some results, and then the hands-on component at the end, if you're interested. Cool. So there's a couple different views of state. There's the EVM model, which is very flat. That's like I have a. I'll move that. Sorry. You have a very flat model, which is, say you have an account address and you want to find the balance of that account, you just like get balance. Or you want to look up the code size of a contract, it's get code size. Or same with storage. You have your contract address and then you have your key and you just kind of do a lookup on that, and it's kind of pretending to be like a single step lookup. That's kind of the very idealized abstract view of state. And then kind of once you go into the EVM, Geth's EVM execution layer, it's still flat, as in it actually does do just a single lookup per state, and that's due to the new snapshots feature. You should use it. And then, but one kind of difference now is that it's segmented out into counts, code, and storage, and that kind of flows from the proof model. And this is kind of the Merkle tree. This is the storage root on each block. And so that kind of has three components. There's the counts trie, which goes from address to the for tuple of the nonce, the balance, a code hash, and then a storage root. And that's kind of the main storage trie. Then kind of code hash just points to some code somewhere, so that's just floating around. That's very implementation defined. And then the storage root is kind of the hash of another trie, and that you have to maintain that trie to be able to kind of do these proofs, but kind of where that is, again, is a little bit implementation defined. And then because those are both like rolled up into the counts, it eventually gets rolled up into the storage root as being able to kind of prove something from there. And then because it's a trie, what that means is if you have a long contract address, you go kind of nibble by nibble, so that's like a hex character by hex character, and then you're kind of following a path through the trie, so you tend to do a lot of sequential lookups. So that's kind of the difference between the flat model, where it's essentially a single lookup from this entire key, versus the trie, where you're going one by one. And do stop me if this isn't making sense or you're not familiar with this. Cool.
The part about snapshots.
Yes.
And you mentioning it's flat when using snapshots and it's unflat when it's not using. Like, what do you exactly mean by that?
So snapshots is enabled. So there's two things to snapshots. There's a sync mode, which is really cool, but then there's like kind of the snapshot acceleration data structure underneath it. And so you can actually disable that, and then it'll go out to the trie every time it needs to do a lookup. So that's kind of why you should be using the snapshots feature. And that also, yeah, one second. Also, this snapshots works really well for kind of the last 128 blocks. And then after that, you actually have to go through the trie to get to historical state. Yep.
Correct me if I'm wrong, but my understanding is like the snapshot is basically a data structure that it duplicates some of the data and it allows for like constant time lookups.
Yeah. Yeah. So yeah, that's kind of what I'm trying to express with this flat, is that it's constant with respect to the length of the key. Sorry, yeah, actually that's a better way to do it. It's constant with respect to the number of keys. I'll talk later about the exact formula on how the kind of number of lookups scales with the keys in the trie, but it's logarithmic for the trie.
I believe that if you iterated through the account space using the trie data structure, it would take like 9 hours or something like that. And then if you iterated through using the snapshot, it would take like 7 minutes or something like that.
Yeah, those numbers make sense. I've iterated through the counts trie before. I don't think I iterated in the most efficient way because it took me like a couple days to get through it. But yeah, snapshot generation, maybe it's a couple days, but it's also doing more work. But yes, working through the snapshots is much more efficient.
What's the key for like a storage key? Like if I want to give the specific storage element a snapshot for a certain contract, is it keyed by the address, or do I have to go to the account snapshot and get a pointer to?
So if you're, we'll talk about this in a sec, but yeah, this slide. Yes, so if you are trying to find something from the storage, first you have to go to the counts, get the storage root, and then go through the storage kind of snapshot system. And it's actually the same with code. If you want to look up the code, first you have to go get the code hash from the address. So actually, well, skipping ahead a little bit, for pretty much every storage lookup, the storage root kind of lookup, so going to the counts to get to the storage root, that operation is essentially always in cache. Like, I haven't seen a single thing where it had to go out to somewhere else to get the storage root, but for something like the code lookup, it'll sometimes have to go out to disk to even get the code hash before it can do the lookup. So this is kind of what we've been talking about. This is the top level, and these are all kind of the cache levels. So following through, like, look through the state objects. If you look for kind of the count address here, and then if it's not, you have to go to the snapshot. So the diff layer is kind of the set of diffs for the previous 128 blocks, because it kind of means that maintains the in-flight set of differences, and it does that so if you need to do a small reorg, that's much cheaper to throw away differences than having to rebuild the entire snapshot structure. And then kind of at the bottom is you have like the full state for kind of 128 blocks ago, and then there's a cache there, and then finally there's disk. It's a relatively large structure. And so for most machines, it's not feasible for the entire thing to be loaded into memory. It's like 20, 30 gigs, kind of ballpark. And then kind of it's similar for storage. Kind of because this is also the execution layer, it holds pending and dirty writes, and then eventually flushes them down later. Same thing, there's kind of like a separate code DB. It has its own, it has a couple layers of cache there, but kind of, yeah, lots of caches. It's important, but there's there. So then for kind of the proof model, we're using Merkle proofs here, and also kind of on the try. I just threw this in if people weren't too familiar, but just quickly go over it. You kind of do logarithmic proof, so it's a lot cheaper to kind of send out like hash 0, hash 1, and then that node. And then if you have the top hash, you can kind of verify everything. And so it's a lot cheaper to hash kind of like a spine of a tree than it is to hash everything. And that's really important for light clients because of the current flat state of Ethereum. It's like 20-ish gigabytes, also in that ballpark. So rehashing that and just even sending that to a mobile client is completely not feasible. And so that's kind of why we have these proofs. And it's kind of been extended a little bit. And then in the future, kind of about this proof model is that there's been look into like Verkle proofs and other ideas around here. New crypto, I don't understand them yet, but I actually really like that we're separating out kind of the execution model from the proof model. So.
Why do you like that specifically?
Because this slide, because every single step through the try, so kind of when you're doing like generating the proof, every single one of these is a lookup onto disk. And so there's like caches, of course, but it's impossible to cache. And then for kind of the scaling time of the lookup with the number of keys rather than constant, it's base 16 because it's a logarithmic tree. And it's specifically log base 16 number of keys plus 1.7. That's empirical. I burned a lot of CPU and RAM to do that, but it actually matches really well. And so for kind of the 160 million keys in Ethereum, that's about 8.5 lookups on average. That's because matched other numbers I've seen. And then because there's another fun twist, and just in general, paths through the try are completely random. It's probably true that the keys that people are looking up are pretty random, but we hash them first, so they're guaranteed to be random. It would be pretty bad if they weren't. And so it's impossible to predict which nodes will be needed. So you could try and predict all of the nodes, but then this kind of view of the state is ballpark twice as large as kind of a flat view. Yep.
Now, correct me if I'm wrong, but when you're saying it could be very bad if they weren't hashed, the problem is that people would be able to say
That is true. Yes. Yes, that's a really good point, that you do need the hashing. Yes. From kind of my perspective of like having to work with this, not hashing is probably nicer, but yes, you can do attacks on this, particularly with the proofs.
Related to that, like using a different proof scheme, how does that, like what they propose for vertical trees?
I'm not an expert on vertical trees. There might be someone here that is.
Yeah, so yes, we can all try and understand vertical trees later, but yeah. So I'm not sure kind of how that would impact it, but seems interesting. Cool. So it's impossible to predict kind of what nodes should be loaded to memory unless you happen to know kind of what key you want to look at. And so we actually do that. So we do a lot of prefetching to load everything into all of these caches prior to execution. And so there's kind of 2 points at which this is done in Geth. The first is during a sync, you have a kind of block executor, pre-executor. So just one block ahead, just runs the block. And then hopefully it's similar enough such that kind of all the states are the same, and it just does that. Fills up kind of the snapshots and like the instant state accesses. And then there's also a specific prefetcher for the try. So you just give it a storage route and then give it some keys to look up. It just grabs them and then throws the value away. But what you've done is you've loaded up all of kind of the intermediate nodes. So when you go back to the previous slide, you're hitting cache rather than disk. And that's 1,000x improvement on every single lookup. Kind of a RAM access, order 100 nanoseconds, an SSD disk access, order 100 microseconds. And it's even worse if you're going out to hard drive, which is why you just can't run an Ethereum node on a hard drive. This latency is killer. Cool. And so that's kind of all of the state models and how everything's worked. So now we want to go back to like, can we make things faster? What addresses are we looking at? So we have to like do a bunch of instrumentation. So kind of the first thing, as part of several things I was looking at, is I wanted to know like which caches were actually being hit. Are we hitting all of these caches? How often are we going out to disk? Does stuff like the prefetcher work? Is that actually where we're spending most of our time? So if you like say, if the prefetcher works, maybe we're not spending more time in execution, stuff like that. And so basically I just did that. I recorded every single location we hit, as well as while I was doing every lookup, I was recording the address of all the count lookups, the count address and hash. So that's kind of the key into the storage, and as well as kind of the code. And then for some of these, there's like separate locations where they're found. And so the way I did this was with using open tracing. So this is kind of like a distributed tracing tool that I just hacked in here. But it works okay. It records spans for operations, so it's really easy to get a duration. So you like start and then you finish, and then with some small amount of boilerplate, it'll just like send that off somewhere. So you get the duration, you give it the name, and then with contexts, you get an automatic call graph. So that's really nice and like works really well out of the box in terms of being able to get this information. And then also you can add key value data. So this pretty much did exactly what I need to do. And then instrumenting it is not that hard. It's a little amount of time and you have to pass contexts everywhere, but once you do that, it's pretty much done. And kind of some of the mechanics is that I collected them with Jaeger. There's other tools here as well that you could use, and then sent them to a Postgres database just to save them all. You can configure the sampling rate. So like if you want like 1 sample a second, you want like 0.01% of samples. These people by default use a very low sampling rate, which makes sense because you're running a lot of data through these. I tried to sample everything. It worked okay. We can talk more about that later, but that was the goal, is trying to collect as much data as possible out of this. And so there are other approaches that you can use here to get performance data. Geth actually has a fair amount of good metrics, especially with metrics-expensive out of the box. Kind of one thing that I'm looking for is that I wanted to trace back specific events, which is hard with metrics. The plus side, again, is they're way cheaper because you're not saving so much data. I have actually like hacked stuff in with logs before. It works barely, but when you need the data, it can sometimes do something. And that's kind of how I ended up on this approach of spans in a database. There are some problems, and kind of figuring out how to do this better is definitely something of interest. It likes to drop spans, which is really unfortunate. So like I tried to collect all the data, but there are specific subsections where it just doesn't have as much. Also, kind of one benefit of dumping it into a database is like certain kinds of queries are really easy. So I can do stuff like set of all of the transactions, or kind of set of all the addresses. So being able to do conflicting queries was a relatively easy task in a SQL database versus thinking of like having to implement a data structure in Geth and like pass everything around to do that analysis. Downside of some of the analysis is that it's harder to do numerical analysis in SQL. So you basically get like count, average, sum, and that's like it. But yes?
Can you elaborate on the metrics for you say no after the fact analysis?
So in the sense that kind of once you pick a metric, you can't like get any more information out. So a lot of metrics are like what's the time spent in this specific thing. So because what I'm doing is I'm recording every single like disk lookup, and then I'm recording a bit of information about it. So I record where it was, also kind of what the address was. So I can do my summation on either of those axes, rather than if a metric, I had to make that decision ahead of time. And so that's kind of what I'm talking about, is you have a lot more data, which is hard to deal with, but you have a lot more flexibility in how you work with that data.
Right. So when you see disk lookup, do you mean level DB lookup or disk lookup? Because level DB under can do also multiple disk lookups.
I mean level DB lookup, yes. Yes, it can do sometimes. There's argument for thinking about level DB in this case, but yeah, in practice, I like to assume that the layers beneath me work pretty well. I thought about trying to include every level DB cache, but that would have been a lot of work. Also would have been fun is all the Bloom filters, but it's already kind of complicated enough. And then like just even moving, like the problem, like level DB does multiple lookups. It also does caching. But one of the things with how Ethereum just uses state, it's a lot of really small keys jumping around. So a lot of these database systems are more optimized for like larger chunks of data. Like you'll typically have a page of like kilobytes. So we're looking at bytes at a time. So being able to implement our caches, we can probably do better than level DB in this specific instance.
For the metrics you use the Prometheus endpoints, I assume?
Yes, yeah. I think so. There's a couple ones, but yeah. So kind of looked at the very bottom, like all the disk layers, and also kind of, because this is the thing that I'm going through, is like, where are we spending our time processing blocks and syncing? So kind of the top level, it's block insertion. That's kind of the my root of all time. There's some, I think there might be time spent elsewhere, but this is kind of the time that I'm looking at, the world I'm in. So I record the block number here, and then kind of the three main functions underneath it. So you process the block, then you validate the state, and then you write the block to disk. And then inside processing the block, you apply all of the transactions. So I also record the transaction hash there. Then you kind of finalize it, which does the intermediate root step, which kind of has to apply all of the changes to the try. So kind of while you're applying the transaction, you're still in EVM execution land, which means you're working with the snapshots. But then once you need to get to the end of the block and finalizing it, you need to be able to show people what the storage root is. So you then have to go through the try and generate all those new nodes. And that's kind of where you're flushing the storage, and then the counts try has to go out to disk to load all those up, make the modifications, and then at the very end, you just go through and hash everything. And that actually turns out to be pretty cheap. That's kind of the top level. And so going back to some boilerplate, this is pretty much all it took to get Jaeger set up in Geth. A little bit of configuration. I think if you're smarter, you could also pull it in from env, like pretty straightforward, set a global, just main entry point. And then using it is similarly easy. Create a span from a context, and you finish the span. And then if you want to set a tag, you set a tag, pass the context around, and it like call graph, perfect. And so that having like this specific ID call graph is also nice because some functions like intermediate root are actually called from multiple places in here. So in addition, it's called invalidate state, but because you have that call graph kind of back up to specific spans, I can look at intermediate roots where the parent function is finalized very easily, and that's different from intermediate root where the parent function is validate state. And that's actually something that would be harder to do if you just threw a metric inside intermediate root. And like if you just like aggregate all of the intermediate roots, you'll find probably that like it's a very kind of disjoint distribution because you have a bunch of them that are really fast and a bunch of them are really slow. And that's based on where they're getting called from rather than kind of inherent properties about the function. Cool. And then there's kind of the methodology slide. 16 core, 64 gig RAM cloud machine. Geth was only using like 10-ish gigs of RAM. I was using kind of default settings for this. One SSD for Postgres because I was just running everything one on the same machine, one for Geth. It is good to split those out into different disks because both of those operations really hammer the disks. There's a GitHub link that I'll have again. That's kind of my fork of Geth and the instrumentation branch. Jaeger tracing is kind of what you can do, is how you set that up, and there's kind of guides on like how to set up the collectors and the agents and whatnot. And then I actually have links on kind of what I used inside the GitHub repository. There's links, yeah, and then lastly, you have to get like a specific plugin to point it to Postgres, so that's the one. Cool. So the fun part, at least the fun part for me, results. It's also the fun thing about research is you don't know what's going to happen until you do it. So this is kind of the top level functions of, so these numbers are relative to the top, so like 100% of the time was inserting block. That's kind of all the time in the world was at there. And then, so these numbers also include subfunction. I hope this makes sense. So like 15% of writing the block, 15% of certain time spent inserting blocks was spent writing it, and like, but only 0.3% was hashing. Does numbers make sense? Cool. So kind of, the first thing that really surprised me was actually how long writing the block to disk took. Kind of assumed that would be faster. That's kind of one area where you could probably put that somewhere else. Talk about that later. The other thing with processing that was hard to work around is applying transactions really was where kind of span issues and data collection became a little problematic. So kind of if I sum up all the time that I have records for, it's only about 3% of the total records I have for inserting blocks, but I think it should probably be closer to 24. And then doing the hash was much more of the time than I expected. That was like really surprised me, it being about like half the time was just loading up the try. I feel like I could have expected it, but I kind of assumed more time would be spent actually processing the transactions. Yeah.
Say that again, sorry. I just go, yeah, maybe just repeat.
Yes. I assumed more time would be spent processing the transactions rather than in loading all the items from disk. So there is a prefetcher that is supposed to help with loading items off the disk. So as you're kind of block executing in the background, every time you do a lookup to hash, it sends it through the try prefetcher. And so that tries to load everything up. And so when the prefetcher is working well, it really does speed up intermediate route, but at least in this context, it wasn't working as well as I think it kind of should, or I'd like to, because I think I'd like to spend less time there.
And is this using the snapshot or not using snapshot?
So this is all using snapshots, but so this is actually a fun thing is when you introduce snapshots, you really speed up your reads during your lookups, and that was actually what saves us from this like state DDoS attack, which just does a huge amount of reads. But then when you go to do the writes, you have to do the lookups as well, and that's kind of what this is showing. And so there's a little bit of work being done to try and like get a little bit ahead on those writes by loading those nodes, but it's not kind of working as much as like it would be nice to, because we're still spending a huge amount of time waiting for nodes and waiting for disk.
And those writes, are they happening as the block is executing, or are they happening at end? Or?
Sorry, yes. So this is about the EVM writes.
EVM writes.
Yes.
Okay.
So the EVM writes, you have to modify the state, and then you have to do that proof. And so you don't prove it with snapshots, you prove it with this try. So we still maintain the try and have to go through and fix everything up. And so now we're spending most of the time kind of fixing up the writes there.
And how much time was that taking?
About half the time of like total block inserting was going through and loading up these nodes. I think 100 to 200 milliseconds could be typical for intermediate route. There's some variability there, but that's kind of the ballpark.
When we were talking about writing the block, it's just writing the RLP input block at the end to the database?
Yes.
Or is it more?
I think there might be a couple other things in there, but yes, kind of everything that's around persist this block.
Yeah, but that seems just like a single operation. The only difference is that the value there is bigger than the other one, so it probably triggers like two-level compaction underneath. But
That could.
like 15% seems like a lot here.
Yeah, and this is, we'll go into this now. I think this is something I'd have to look in a little bit more, but my bet is that this could be done async and kind of on its own thread, because I don't think the next block is actually waiting on the result of that write. And so that's something where you could get a pretty easy benefit from doing that. Well, this is like only for syncing essentially, but something you could do. Yeah, so this is also the summary. Kind of have to go between the two. Yeah, and then like this, like it's definitely dropping spans. Like when I looked at a block number versus the number of transactions, it's unfortunate. I was really hoping to get everything, but it's life. So now this is, I think, the really cool part to me. Is this cache misses during the execution itself. So it turns out the pre-executor is doing a really good job. It also turns out that like the small percent of misses really take up a huge amount of the time. So kind of whenever you're looking up like an account or a state access, like 1.5% of the time you actually have to go out to disk, versus like 75% of the time is spent on those operations. So that's 75% of all time spent on lookups is spent going out to disk. So it's really this huge asymmetric thing where if you can push the prefetcher and other tricks to get everything into RAM, you've cut your lookup time by a huge amount. And then when compared to kind of EVM time, about 40% of EVM execution is waiting on disk, so waiting for these things. So it's not quite as a big a deal for when you're looking at total EVM execution, but it's still, that's a fair amount. And it's just kind of like figuring out how to do this would be fantastic. And then kind of the last thing for the number of samples, I had 600,000 lookups that went out to disk out of the 16 million. So even though I'm like dropping some data, the huge amounts, I think it's relatively good. So in all of the various like other sub-slices that I've looked at are kind of similar for like prefetchers working, pre-executors working, but the last little bit is really slowing everything down. And so kind of back to intermediate root again. Yeah, so median 120, so these are kind of like stats on it. So when I was looking at how the prefetcher was working, first I was like a little surprised about this. I was like, okay, is the prefetcher doing what we expected? And so going back to how it works is that it has a bunch of keys and it just looks them up. So what I did is I recorded the number of keys that it was able to look up, and then when it got closed out, I looked at how many keys it still had left. And you can kind of see like it's getting most of the keys, but there are still some keys left. And there is kind of correlation. Kind of the scatter plot, it's not perfect. And good time to do a regression, but there's kind of a little bit of a trend between this. So on the bottom is duration. It's in nanoseconds, but these that's a 1E9, so these numbers are seconds. And then kind of up here is the total processed. So up to like 2,500 different keys over a block, but it's kind of more clustered down there. And then here's the total amount of keys left. So overall, and then there is like a fair amount of time where we're like getting to every key. I haven't figured out for which blocks and kind of why the prefetcher is working in different ways. But because one thing that it does do is that because it's just getting values sequentially, the prefetcher is sequential, and that's probably one area of improvement. That kind of as soon as you have a node, you can also kind of go down all subpaths of that in parallel. So it's a little tricky to actually implement well, but that's kind of one thing where you don't need to wait for each result. Yeah.
Probably. Okay. Are these updates are these updates being executed in parallel? Do you collect a bunch or batch updates? Right? Are these batch updates too?
I guess it's in a batch, but it's running one after another, because.
Oh, it is. It's
yeah.
running one update per well, as you're going up, I guess. Yeah. Okay.
Maybe we can talk in a second.
Yeah, we'll talk.
Cool. And then also one of the crazy ideas, actually going back to the start, was like, what happens if we just parallelize transactions? And so how often are we reading from not only the same contract, but the same storage inside that contract? So this was one area where I would have liked a lot more samples. And I actually have the data, but like actually wrangling it out was hard. But so kind of looked at a histogram of like the total number of transactions per block and the total number of conflicting transactions per block. And so we find here is that it's, I don't know, like 10 to 20% of transactions in a block will have a conflicting pair of address and hash. So it's not zero. So people are interacting with the same smart contracts, but it's also not hugely high. And this is also ignoring the problem of is the second transaction doing something different based on the first transaction. So this is, if two transactions read the same data here, it would record as a conflict. So there's ways you can be smarter here. So this is just kind of the start. And the last thing is not only if one of the problems that for this that I think we need to look into is that even if so if you have a first transaction and then the second transaction goes to the first transaction and say that stores like which smart contract you should go to, and that changes in the first transaction, then when you go to the second transaction, you have to do the first load, then the second load, and so that gets you away, and then that could potentially be out to disk, and so that's kind of a data dependency between the two. That's very hard to work around in terms of making it performant. Because even if you have conflicts, going back to the start, you may not have that data dependency, which means you can keep it all on disk. And so I'd like to have that data on, are there these dependencies? But that's kind of the future research. So yeah, yeah.
Sorry, I just have a quick question.
Yeah.
In your overlap, do you count touching the same contract as the same state or only storage slots?
Only the same storage slot in the same contract. Yes.
Cool. And then the other question: have you seen the speculative, EVM speculative execution paper thing analysis? I don't remember
Rain
it for a
block
while.
or something else?
There's like an active paper that came out where they modified the attempt to do speculative execution. What they found was that earlier in the chain, it was a lot easier. And as there's more composability and stuff, it became more difficult.
Interesting.
But
Yeah.
it's interesting because you sampled this from relatively recent logs.
Couple years ago. So this is about. Oh, wait.
This was 8 million.
Yes, somewhere. Yeah, sorry, I missed this. Yeah, so around like 8.5 million was where these samples were from. It's
I've executed those in current and they're very different.
Okay.
yeah,
Okay.
it's possible that some of these.
And stuff.
Yeah. Yes,
Yeah.
I was kind of just like running a sync and trying to get as far as I could, but yeah, I haven't seen that paper. That'd be super interesting, and I could believe it that it definitely does change, and that's kind of yeah. MEV is doing MEV.
Just curious why you selected this range.
Because that's where the syncing node ended up.
That's fun.
Yeah.
Why you ended up there to just not go further?
Well, so I mean, that's where kind of ended up in time to get like all of the data. Like I want to like do more and like go further, but that's only do what you can do.
And all these insights are only from tracing, right? Only from length traces, and then I'm doing analysis on them.
Yeah.
That was the only one.
But also the other one in which the transaction count versus conflicting counts, which should be a separate one, or the analysis.
It's from the traces,
Oh,
yeah.
from the traces.
Yeah, so that's how I got the data and then kind of did the analysis later.
It would be interesting to see if conflicting transactions happen more often at the beginning of the block, where flash boys are ending transactions.
Yes.
I
Yes.
actually ran some analysis on that. So I worked at Fashots and I looked at like conflicting state in the boundaries, and I found that not that many bundles clash in terms of what state they clash, surprisingly. When they clash, it's mostly in wrapped ETH. If you take out that and the Coinbase also, because of the error paying, it's very minor. So I was surprised about that. I have that on my GitHub actually.
Cool.
It'd
Pardon?
be interesting to have a public data set, like person we sync
No,
the node,
that's a great question. No, I
and
didn't.
then export the data in a public data set.
Yes.
It's huge, of course.
Yes, I'm not sure how to explore. Like, I don't know. It's about to be lunch relatively soon, but that's part of the plan for the workshop was to make this data available so you can like query and look through it and whatnot. Cool.
Can I have a takeaway like composability comes at a price?
Sorry, I just want to say that I think that the reason why state access overlaps so much is because fee pricing does not account for parallelism. So if you adjust fees so that transactions that are parallelizable are cheaper, then that's a natural incentive to allow for parallelism. Right now, there is no such incentive, and so of course you find tons
Yeah.
of conflict.
Yeah.
The access list, no? The access list.
Yes, exactly. That's a step in that
Yes.
direction.
Yeah, and so access lists are cool. Kind of one of the other, so some of the takeaways already talked about, like move out the right block with state. Something about the access lists is that like it's a step in the right direction to being able to make sure that every single lookup is hitting RAM rather than disk. But one of the problems there, I think we'll see, is that with the EVM, it's kind of, you're trying to constrain a very Turing-complete language. and so doing that is hard. I think with access lists, you could still be useful, but this is kind of another area that's interesting to look in, is look at every single lookup and then look at the value. It's hard. You have to trace kind of the provenance of every single value and say, is this a value that came from state, or was this a value that was passed in? And that can, and for some of the values that are pulled from state, you can kind of do access lists, but that makes it harder to do access lists versus if you pull in kind of every potential lookup from the actual transaction itself. And those are kind of two slightly different models.
That's so cool.
Cool. Yeah. Yes. These are kind of all various summaries of the talk. A researcher says more research is needed. Classic. Yeah. Again, is it worth? And then I think a big part of this is that asking ourselves, like, we could constrain the model. It would probably be better. Is it kind of worth that effort? Like, what are the steps that can improve the execution performance without having it be a giant hurricane task? And then also the last thing is, you do all this work, more transactions. Now you just have state growth historically, and so figuring out how to do that. Cool. So there's supposed to be a question slide, but everyone's asking questions. Here's the GitHub repository again with the branch. Work at C Labs, we're hiring for work in this space. If you're interested in working on Geth, you can talk to me later. And also, I guess, back to questions. Or not if people. Yes.
Could you put most of the state to memory, and how would you then get the speed up with this, or would it be better to like put everything if I would like that?
Yeah. So the problem is that it's not really feasible to put everything in memory. So I've looked at this a little bit in the past. The current size of kind of the current state is about 20 gigs unoptimized. I think you could get it down to maybe 12. But then like 12 is hard to do because Geth is already at like 10 just doing other stuff. So kind of it's basically, I think, unfeasible for like a consumer node to have enough memory to be able to load everything. Kind of like, this is kind of like the Solana model where it's like huge specs, put everything in RAM, like how long until they start requiring Octane, like all of these like really expensive things that you just can't require from a consumer.
Just out of curiosity, do you know if Geth has any like trivial configuration to do that? Or is it going to be like a little bit of a non-trivial, engineering thing to like throw everything in memory and see what happens?
Yeah, you could try seeing if there's like a snapshot memory limit and setting it really high. There's a couple various memory limits. I think the snapshot one would be the most interesting. I don't know if it would prefetch the snapshot into memory. So kind of that's one area that you could try.
Cool.
I actually didn't understand how the prefetcher works because you execute the block and you record what get fetched, but then you just execute the block. So where is the pre here?
So the pre-executor, so you kind of have a list of blocks, right? So you're about to process one block, save the results, but right before that, you check if there's a block ahead of the block you're about to actually execute, and then on a different Go routine, just run the block and throw away the state transition. So then it does all the loads, and because of the shared snapshots, kind of the lookups it does hit to disk. And that actually might be kind of one proxy for how much data-dependent loads there are, because it's basically running on a previous state. And then once it moves on to the next state, then it kind of does a slightly different set of loads. Does that make sense? Do you want me to try to explain again?
So we are talking about the sync into that, or we're talking about state up to sync on the sync?
syncing a node.
Okay,
Yes.
syncing a node. So we have all the blocks, and we know that we have the next and the block after that.
Yep.
And we executed that. So we have the state in the disk or whatever, and we have this like new dip of the state that's still in the memory. We still haven't written that to the try.
Yep.
And now we execute the child block on top of that, so it heads probably into some of those state diffs that are still in memory, and that's faster.
So kind of you're executing this, you're inserting this block, but if this is kind of the child block, you're on the side running this block against the previous state.
Okay. Gotcha. Okay.
So,
Thanks, Joshua. Sorry, it was an awkward silence. So I
No, that was great.
yeah. How's their lunch?
Yeah.